I see that there are at least 4 correct submissions, but rest of them still have trouble. So what I'll do is I'll go over through some portion of the solution to give you that wow factor. Oh, I mean, it was easy, and then we'll move from there.
Is this going to be in the plasticity and structural problem section?
Can you?
Plasticity and structural problems, is that the topic?
Well, not really, because I still asked you to apply Euler-Bernoulli beam theory.
Okay.
So in plasticity, you will be expected to know problems where you have a perfectly elastic and then perfectly plastic system.
Okay.
So that's a little different than having a cubic nonlinear constitutive law.
Thank you.
So, so for example, this was our problem, right? And then our constitutive law is E times epsilon cube. Okay, so first of all, whoever started by writing H33 is the moment expression. This term H33 cannot be defined for this system like integration of E x2 square d x1 0 to L. This is not correct, because the basis of this expression was a linear constitutive equation, right? So we have to find this expression again or just evaluate that expression. So as discussed in last class, M3 is integration 0 to L sigma 1 x2 dA, right? And now sigma is E times epsilon cube x2 dA. And we have a negative sign here. Okay, so epsilon for this problem, we have a transverse shear force at the tip, so it would not induce any axial stresses, axial strains. Go ahead.
How are you integrating from 0 to L with respect to dA?
Oh, yeah, that's integrated over the area. So epsilon here is minus x2 second derivative of displacement with respect to x1. So it's the term which is kappa 3 or k3 x2 k3 term. The rest of the terms will not show up in the strain expression because the force applied is a vertical tip shear force, right? So if this is my coordinate frame, my cross section will look like I2, I3. This is my H, and this is the dimension B, right? So I will substitute this expression here and try to integrate over the area. And there was a negative sign on top. So what I essentially get is integration over the area E x raised to power 4 dx2, and then this term is only dependent on x1, so I can take this term out of the integral, and that term becomes d OQ, right? I think almost everyone figured at this till this point in their solutions.
And you take out B too, right? If you're removing the...
If I'm integrating with, yeah, let me just write that it's still an integration over the area, because I have integration over the area. Okay, so let's keep going. Simplify this expression, separate dA into dx2 dx3. So there will be a double integral over the area. The limits will go from minus b over 2 to b over 2, and then minus h over 2 to h over 2. So finally moment expression will be E times b over 5 okay. So I think this part is also correct for most of you. So how do we go from here to finding the displacement at the tip? We know that if we make a cut here, we can calculate moment at this point to be PL minus x1, and we have a moment expression here, right? So P times L minus x1 is equal to EB over 5 times h raised to power 5 over 16. This is your second order differential equation based on equating the moments. So you can now use this equation to solve for u2. So you'll get so if you integrate this equation twice and apply the boundary condition on the left end, the slope and displacement 0, because we have a cantilever condition here. So displacement at 0 is 0 and the slope at 0 is 0, right? So if you apply that boundary condition there, integrate this equation twice, substitute L in respect to x1, you will have your answer. So if you have a simple problem like this where you have just one load or a uniformly distributed load, instead of going to the fourth order differential equation of displacement, you can use the second order differential equation with respect to moments. If you do that, then you will be able to skip the natural boundary conditions, the moment and the shear force, because essentially what you do, you take this equation, you differentiate it twice, and then you integrate it twice again to solve for displacements, right? You don't need to do that for simple problems. But if there is a problem with discontinuities or additional supports in the middle, then you would have to do that so that you can take the displacement values from one segment to the other segment as continuity relations. Okay? Any questions on this? Yeah.
For the strain field, why don't we consider the other terms?
So we know that the other terms are contributions due to bending about the other axis, which is about I2. So this one is inducing bending only about I3, right? So this one will give an anti-clockwise moment, so about I3 there is a bending.
Right, but
The other term is for bending about I2.
how can we be sure? Because here the material is different, it's not, we can't use the Huxler, right?
So material is uniform and this section is symmetric. So it will not induce bending in the other direction if you have a perfect shear force applied at the tip, right? Because that property is kinematic. In the strain expression, we have not introduced any material property yet. So whatever you calculate here is kinematic. So if you have a shear force applied, if there is symmetry, there won't be any coupling in this expression.
Thanks.
Make sense? Looked easy now? Not in the exam. Yeah. Okay. So remember, for simple problems, you can make your life simpler by just using the moment expression, integrate it twice to get the displacement.
So as a question,
Yes.
with that definition of strain, I thought we defined in the strain tensor that we had the displacement divided by the derivative in the same direction, so it would have been partial u1 over partial x1,
Mm-hmm.
and then you would go in the 3x3 matrix. How is this strain different from that strain?
It's the same because you have partial u over partial x1. In this case, you have u1 as the variable of x1, x2 and x3. So that's 3D displacement. And then for Euler-Bernoulli beam theory, you discretize this 3D displacement as u1, x1, x2, x3. And then you say that this is contribution from the axial displacement, which is u1 dependent only on x1, and then you have contribution from the bending in about x2 and then bending about x3. So I substituted that expression here, so you get the strain expression which has curvatures in it, right? So what I'm doing is I have a perfect shear force. I know that some of the terms are going to be 0 in that expression, which contributes to the axial strain and the strain induced by bending in the other direction, bending about I2. Yeah. So it's the same thing, but it's just that we have converted the 3D problem into 1D problem. So we are getting some information by making some assumptions. Okay. So coming back to the virtual work. So in the last class we discussed that there is a concept called virtual work, which we can use, and it is based on Euler's first, second laws. So a system of particles would be in equilibrium if the virtual work done by the externally applied loads is 0, right? And that's the principle of virtual work. So we'll pick up this concept from an example. Let's say I have a mass which is lying on a flat ground with friction, and I'm applying a load P horizontally. So let's draw a free body diagram and the coordinate frame. So let's say this is my I1, this is my I2, and so this applies an mg force due to gravity. You have a P force applied externally, there is a friction force F, and then there is a reaction force on the mass by the ground. So through virtual work we defined that sum of all the forces on the body owing to virtual displacement vanishes for equilibrium, right? So let's do that. I have my virtual work, which is mg real force but a virtual displacement in I1, so delta S1 virtual work plus minus r times delta S1 plus P times delta S2 minus F times delta S2. Why did I consider forces in different directions? Because when you calculate work, it's a scalar quantity. It is no longer a vector quantity. So you can add the work done by all the forces within one expression, right? Now I'll just club the terms. I have mg minus r delta S1 plus P minus F delta S2. And by definition, virtual work is 0, so this expression should go to 0, right? Now, we also discussed that S1 or delta S1 and delta S2 are small virtual quantities, so they can be arbitrary, right? So, if this expression has to go to 0, these two are arbitrary, so this expression and this expression has to go to 0, right? Make sense? Okay. Now, this is my equilibrium equation, and this is my constraint equation. So, by writing virtual work or principle of virtual work, you can obtain both equilibrium and constraint equations from the system. You can also see that we have flat ground, a displacement along I1 is not feasible because of the ground. So, if we consider a virtual displacement there, it is basically a kinematically inadmissible displacement, right, because you have constraints. So, delta S1 is kinematically inadmissible and delta S2 is kinematically admissible. So, from this exercise we can find a couple of things. One is that if you just need the equilibrium equation, you do not need the kinematically inadmissible displacement. You can just take the contribution of virtual work based on the kinematically admissible displacements, right. So, for equilibrium, we need to account for the virtual work done by kinematically admissible displacements. And if you account for kinematically inadmissible displacements in your virtual work expression, then you are going to get constraints or reaction forces. So, if a problem asks you to evaluate equilibrium equation or asks you to find any force expression, then you do not need to consider kinematically inadmissible displacements. You only need kinematically admissible displacements. But if you want to find reaction forces, you can just consider the virtual work done by kinematically inadmissible displacements and you will find your reaction forces, right. So, based on what you need, you can tailor your virtual work expression to evaluate that value. Okay, so let's visualize what work is. So, let's say I have a linear system and this is my force for a displacement u, right. So, if I have a virtual displacement, essentially this will be my virtual work done. And this triangular region here is essentially work done by the force. Okay. So in a similar way, I can define complementary virtual work. Complementary virtual work, which is denoted as delta W prime and is equal to a real displacement times a virtual force. So we used virtual work to identify our forces through equilibrium equations. We can use complementary virtual work to identify displacements because we have real displacements there. So let's say if there is a problem and we want to find out displacement at a given point, we can use complementary virtual work and evaluate our displacements. Okay. Some more observations. Let's say I had a nonlinear system now with force and displacement. So the work done by the force is not the same as the complementary work done. So in this case, even the virtual work done is not equal. Whereas in case of a linear system, the virtual work done is equal to the complementary virtual work. Okay, so let's talk about virtual work and complementary virtual work. For beams in bending or beams in general. So let's talk about beams in bending, axial loads, torsional loads. Okay, so let's say I have a beam which is undergoing an axial load N1. Okay, so if I cut an element here, the element would look like under tension. So it would have axial forces which are pulling the element from both sides. So the internal forces in the element would be in this direction. So now if I want to write the virtual work done by the internal forces, I have my displacement u, and at this point my displacement is u plus du over dx1 times dx1 if this length is dx1. So the virtual work done by the internal forces, not the external, the internal forces on the small infinitesimal element is integration n1 x1 times u, this force vector here times the displacement at this point u, minus n1 x1 times the displacement at the other point. So u plus du over dx1 times dx1 right. So if I cancel out terms, this term cancels out with this term, so I'm left with integration of n1 x1 du1 over dx1 times dx1, integration 0 to n. Okay, and we know that du1 over dx1 in case of axial loads is epsilon 1, right, strain. So we have work done by internal forces as integration, and I missed the minus sign here, so negative of n times epsilon 1 n1 x1 times epsilon 1 dx1. So this is for,
Show me where you put the minus sign.
yeah, the minus sign in this expression. Thank you. Okay, and this is for beams in axial loading. Right. So I can have similar expression for beams in bending and axial. So that would become m3 k2 x1 plus m3 k3 dx1. So the axial loads, then we consider the bending about I2, and then we consider bending about I3. So the total virtual work done by internal forces for a beam under axial and bending loads can be written as this.
Is that M2K3? Or no?
Yeah, it's
Oh, okay.
m2 k2.
Thanks.
Yeah. And then we can also write the complementary virtual work as so in this expression I have n1 x1 and then the virtual quantity epsilon 1 dx1, because my displacements here are all virtual quantities, right. I'm calculating virtual work done, so my strain here is a virtual quantity, and if I write my complementary virtual work done by the internal forces, then it will be virtual forces in this case. So I have epsilon 1 times delta n1 x1 and then I have k2 times delta m2 x1, and then I have k3 times delta m3 x1 dx1. So these are all virtual quantities. The strains and curvatures are virtual, and in the complementary virtual work you have virtual forces and moments. So these expressions become very important when we try to solve a problem using unit load method. So unit load method is or unit load method can be used to evaluate displacements in a given system when you have externally applied loads. Okay, so can be used to evaluate displacements. And we'll make use of the complementary virtual work for the unit load method. So for a system to be in equilibrium, the complementary virtual work should be equal to 0. Complementary virtual work is the work done by real displacements and virtual force, and this can be divided in two parts. One is external and one is internal. So we get the external complementary virtual work plus the internal complementary virtual work is 0, right? How does this equation come from? Like, where does this equation come from? The Euler's first law, right? So we discussed this in the last class. For a system of particles, we wrote sum of the forces plus sum of the internal forces equal to 0. So the sum of the external forces, work done by those, will be part of this, and the sum of the internal forces, the work done by those, will be a part of this. So if we have n particles, this was the sum of all external forces, and then we had a double summation of I1 to n, j1 to n, where j is not equal to I, and these were the internal forces. So this expression was discussed in last class as Euler's first law. Now if I want to calculate the complementary virtual work, then I would just evaluate or treat them as virtual forces and have real displacement. So u times variation of external forces times variation of internal forces, and then again displacement, right? So this is my virtual work done by externally applied loads, and this is virtual work done by internally applied loads. So you see how this expression comes up using Euler's first law. And now we already know how to calculate our internal virtual work, complementary virtual work. That comes from this expression over here for a beam in axial and bending. So let's say I have a problem where I want to evaluate displacement at a given point. So that displacement is real displacement which is happening. So let's say that the displacement is delta and is caused by a virtual force which is delta d. So this will be my virtual work, complementary virtual work done by external forces, right? External complementary virtual work. A real displacement, which is my unknown, and a virtual force. So I can substitute this in the previous expression where delta WE prime is the complementary virtual work done by internal forces. So delta times delta D is equal to, there is a negative sign already in this expression. When I substitute it here, I get integration epsilon 1 plus K2 delta M2 x1 plus K3 delta M3 x1 dx1. Okay, so for a given system, if I can calculate my stress resultants, then I can substitute the values in this expression, and this is a virtual force, and I have the displacement as unknown, which I can calculate, right? And I also know that my strains and these curvatures are done or are generated in the system by the real forces, right? And those real forces are N1, M2 or M3. So I can rewrite this expression as delta times delta D integration N1 x1 over S times delta N1 x1. This is for the axial. I wrote the expression for strain in this expression. So strain is N1 x1 over S for the axial strain. Then I have my curvature, which is M2 x1 over H22 I'll write this expression over there. Plus M2 x1 over H22 plus M3 x1 over H33 times delta M3 x1 dx1. Okay, and then I can also simplify it by taking this delta D and dividing this entire expression with delta D. So I'll get now, if you see that this is a real quantity and all the quantities with variations are virtual quantities. Okay, so for a given problem we need to evaluate the real quantities and the virtual quantities. So let's take an example. I have a cantilever beam, okay, and I'm applying a P load on top at the tip. and I want to evaluate the displacement at the tip. So I can make use of my complementary virtual work and unit load method, which we just discussed. So what I need to do is evaluate the stiffness constants for this beam so that I can put the values here in H22, H33 and S. So the first step is to evaluate the stiffness constants. So let's say it's a rectangular beam with width B and height H. So those constants would be very simple to evaluate. S will be just E times area, H22 will be E times BH cube over 12, and H33 will be E times HB cube over 12. Right? So if you have a different cross section which is not symmetric, you would have to evaluate these constants, and also you'll have H23 in the expression. Okay. Now we need to evaluate these real quantities and the virtual quantities, right? So the real quantities can be evaluated by what the externally applied loads are, right? So P is externally applied load. Based on that, I can evaluate my N1 x1, M2 x1, M3 x1, right? So this is not an axial problem, so this term will go away because these are the contribution of axial forces only. And then if my coordinate frame is I1 and I2, then I have moments about I3. So this term will also go away because this is moments about I2, and then I'm left with this term, right? So I have delta is equal to integration M3 over H33 times delta M3 over delta D. Okay, so I need to evaluate two things. One is the real moments which are generated by the force P, and one is the virtual moment by the load delta D, which is the virtual force here, right? So I know that moment M3 can be evaluated by just making a cut in this expression. So M3 of x1 is equal to P L minus x1, as we saw in the problem which we just solved in the class. This is due to real forces. Now to evaluate the expression with virtual forces, I would assume that I am applying a unit load delta D. So at the tip I apply a unit load. So what I have to calculate is the moment due to this unit load, and that will be my this term, right? So I calculate the moment, which is my virtual quantity, is equal to 1 times L minus x1, because this is my moment generated by a unit load at the tip. Okay, makes sense? Moment by a real force, moment by a virtual force of a magnitude 1. So in this expression I can say my delta M3 x1 over delta D is equal to L minus x1. Sometimes this also is represented as M cap x1, just for the sake of simplicity. So this expression will essentially become integration m3 cap over h3 dx1. Okay, so now we have calculated m3 cap, we have calculated m3, we know what is h33 if we substitute everything in the system integrated with respect to x1, we will get our delta. Or yeah, okay. So now few things to think about. If the system is not if the system has a section which is not symmetric, then you have h23 terms. So the expression which we used initially, where we are substituting the stiffnesses as S h22 h23 or h33 will change because it would have contribution of h23. And now this also assumes that the constitutive law is linear. So what happens when it's non-linear? E times epsilon cube is the stress. Can you evaluate this entire thing and find delta? Yes, you can do that. So now you can check your answers by solving this problem using Euler-Bernoulli beam theory and using virtual work. So we'll stop the class here today. There is a short survey for you from the Center for Teaching and Learning, and I'll help distribution in distribution of the forms. If you have any questions, feel free to ask me.